Connection to thermo. What we know.
Delta G must be less than 0 for a reaction to proceed in a given direction. And delta G is the maximum amount of work that can be done by a system.
What we will learn today.
A system is at equilibrium when it is no longer able to do any work. For example, delta G equals 0. And the constant for equilibrium is directly related to delta G.
What we can tell from delta G.
When delta G is greater than 0, the constant of equilibrium is less than 1, which means that the extent of reaction at equilibrium is mostly reactants. When the delta G is greater than 20 kilojoules, the equilibrium constant is much less than 1, which means it's virtually all reactants. When it is less than 0, the equilibrium constant is greater than 1, which means it's mostly products. When it is less than negative 20 kilojoules, it is much more greater than 1, which is virtually all products.
Now for our problem.
Propane C3H8 is a hydrocarbon that is commonly used as fuel for cooking. Part A. Write a balanced equation for the complete combustion of propane gas, which yields CO2 gas and H2O liquid.
Because you have to balance your equation, your total equation will be C3H8 plus 5O2 yields 3CO2 plus 4H2O.
Part B. Calculate the volume of air at 30 degrees Celsius and 1 atmosphere that is needed to burn completely 10 grams of propane. Assume that air is 21% O2 by volume.
You will use perverted NERT to find the volume of this equation. But before you do that, you need to convert the 10 grams of C3H8 into the moles of O2. So, because we are trying to find the volume, you're going to plug in your numbers. 1 times V is equal to 10 divided by 44 times 5 times the constant, which is 0.0821, and times the temperature change, which is 30 plus 273. You then get 283 is equal to 0.21x. You isolate x and you get 135 liters.
Part C. The heat of combustion of propane is negative 2,220.1 kilojoules per moles. Calculate the heat of formation, delta H, of propane given that delta H of H2O liquid equals negative 285.3 kilojoules per mole, and delta H of CO2 gas equals negative 393.5 kilojoules per mole.
This is products minus reactants. So it's going to be negative 2220.1 is equal to 3 times negative 393.5 plus 4 times negative 285.3 minus x plus 0. We are trying to find x. X equals negative 101.6 kilojoules per mole.
And lastly, part D. Assuming that all the heat evolved in burning 30 grams of propane is transferred to 8 kilograms of water, specific heat being 4.18 joules per grams times Kelvin, calculate the increase in temperature of water.
You're going to use Q equals MC delta T. We know that delta H is 2220.1 and that is equal to negative Q over moles. Because we are trying to find the delta T, we have to find Q first to plug it in. In your equation, to find Q, you're going to multiply 2220.1 times 30 divided by 44. Your Q is going to be 1513.7. Then you plug that into Q equals MC delta T. One 513.7 equals 8 times 4.184 times delta T. Typing it into the calculator, we get that delta T is 45.2.
I messed up so many times. If you didn't.
And that is it for connection to thermo.